this video, we're going to talk about the binomial distribution. One thing we know from English class, we know about our prefixes here, and when we see the prefix bi, we know that has to do with 2. Okay, our binomial distributions are distributions where there are 2 possible outcomes in our experiment. So when we're talking about binomial distribution in a binomial experiment, we have to satisfy all 4 of these things for it to be considered a binomial experiment. One, is there a fixed number of trials? Usually more than one. If we're going to flip a coin one time, yes, there's 2 possible outcomes, but that's not very exciting. Maybe I want to flip my coin 2 times or 3 times or 4 times, and we've drawn pictures of that. Maybe I want to flip it 25 times. That tree diagram would get pretty hairy. When we're talking about each trial, it can have only 2 possible outcomes or be reduced to 2. One of them we consider success, whether it's truly a positive thing or not, but one we call success and the other piece we call failure. So maybe I consider flipping head a success, or maybe I consider flipping a head a failure, but it can be 2 possible outcomes. The outcomes of each trial have to be independent of each other. So if I'm drawing a card out of a deck and then I replace it and draw another card, that's allowed. But if I draw a card and I set it aside and go back for the next one, what I drew the first time affects the probability of the outcome of the second, and therefore those guys aren't independent. But if I flip a coin, whether I flip it 1 time or 110 times, the probability of getting a head each time remains the same, and the probability of getting a tail remains the same. The probability of success has to be the same for each trial, so those 2 things kind of go together, what I was just saying. So 2 possible outcomes, or reduced to the idea of kind of a win or loss, or succeed or fail. Outcomes have to be independent, and the probability of success is the same every time. So let's talk about these things here on the list and decide whether they fall into our categories. Hopefully that's not too small for anybody. We just said if we flip a coin and record the result, that's binomial. I flipped it 1 time, which is boring. There's 2 possible outcomes, heads or tails. If I were to repeat that 6 or 8 or 10 or 12 times, they would be independent of each other, and the probability of success of getting a head each time is 1/2 and a tail each time is 1/2. So again, to make this more exciting, maybe I want to say, I won't number it, flip a coin 100 times. Record the result. Okay. Again, we've drawn tree diagrams for 2 flips, 3 flips. I think you did 4 flips on your homework for me. And 4 was tight enough, I think you'd agree. But to try to draw a tree with 100 flips of a coin on there, way more intricate than we could come up with. So we're gonna have a shortcut for we're gonna have a formula for computing that without needing a tree. Okay, so maybe I want to shoot a free throw and record the result. Maybe I want to shoot, instead of a free throw, maybe I want to shoot 20 free throws, and I want to record the results. Okay. So there are a fixed number of trials. 20 times I'm going to shoot that basketball. Each trial can have only 2 outcomes. My free throw either goes in the basket or it does not. Whether I make or miss the shot my first time, the probability of making or missing the shot the second time and the 3rd time and the 20th time, all is independent. Nothing changes there. Okay, the outcomes are independent. The probabilities that I make it each time are independent. So maybe I should check mark these guys that are binomial. Okay, flipping a coin, shooting free throws, record the results, we could count those as binomial. If I roll a die out on the desk and I record what numbers rolled, and then maybe I do it 2 times or 10 times or 100 times, I could fix the number of trials. If I write down a 1 one time and I get a 3 another time and a 6 and then maybe another 6 and then a 4 and then a 2 and then a 1, there's no clear win or loss there. This would not be a binomial situation. Now, I could adjust it a little bit and say, I'm going to roll a die. And I'm going to record what number is rolled. Okay, and I could say that success, or maybe I win the game, is rolling a 3. I could reduce that to 2 possible outcomes. Even though there's 6 possible numbers I can roll, I either roll a 3 or I don't roll a 3. I can either succeed and win the game, or I can not succeed by rolling a 1, 2, 4, 5, or 6. In that case, okay, I can, if I'm breaking it into 3, roll a 3 or don't roll a 3, that would be binomial. Okay, if I just write down, I don't care whether I roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6, okay, not binomial, there's more than 2 possible outcomes. Same thing here if I want to choose a student at random from your class and record their last exam score. So maybe I'm going to pick 5 students and see what your last test score was. There's more than 2 possible outcomes there. There are 100 points on the test. Okay, the scores could be any number of things. Um, they are independent of each other. Probability of success, you could argue maybe it does, maybe it doesn't remain the same. But if I got a little bit more specific and say I'm going to choose a student at random, okay, I could make success scoring 70 or higher, failure being less than 70. I'm almost out of room. So if I choose your name out of the hat, if you scored an 83 on your test that we took the other day, that would be considered success. And less than 70%, maybe you got a 59, that would be considered failure. Now, the parting question here, where we might say, I don't really know if this is binomial or not, is whether the probability of success remains the same for every trial. I guess for each trial it would. Okay, but for each student it'd be different. So we could say, I'm not sure that's completely a binomial experiment. I have a daughter that plays tennis. She has played some athletes that have some phenomenal serving capabilities, and every once in a while they get one of those serves that you just can't even get to or touch. So maybe this person has been working with a pro, and so they have a probability of success. Maybe 1 out of every 20 serves is an ace. They either, in terms of a fixed number of trials, we could say, you know, she served 12 times in a game, or whatever. We could fix the number of trials. Success could be acing her opponent, and failure would be not. Each time she serves that tennis ball, she has the same probability of success, and the outcomes of that trial stay the same. She's either going to ace it or she's not. So I would argue that this could be considered a binomial experiment. Number 6, choosing a card from the deck and writing down what suit it is. Remember, there are 4 possible suits. We have hearts, we have diamonds, we have spades, we have clubs. Whoa, that's supposed to be a spade. I do not draw well on this tablet. I've drawn them better on the board. Wish I was in class with you so I could draw on the board. Okay, but I have 4 possible outcomes here. And so that eliminates me from being binomial because there's more than 2. But if I'm going to draw that card from the deck and say, I'm going to win if it's a heart, and if I draw any of these other 3, then that means I lose. So I have success, and I have failure, and I could reduce that to 2 possible outcomes. Assuming that each time I replace that card, if I'm going to draw a card, look at it, I win if it's a heart, I lose if it's not, put it back in, shuffle it up, start all over again, I have the same probability of drawing a heart each time out of that deck. The outcomes are independent if I put the card back every time. So this would be a binomial experiment. If I keep the card out and do not replace it, then it would not be. So in the next video, we're actually going to compute some of these probabilities, but I wanted to take a substantial amount of time to make it clear what's binomial and what's not. So stay tuned.